All right. Welcome to this new session of the FCAI Coffee Seminar, and we are really excited to have here with us Kai Nordlund. Kai is a professor of computational material physics, and at least for the rest of today, the Dean of the Faculty of Science at the University of Helsinki, and from tomorrow will be Vice Rector. And so Kai has been doing a lot of work, of course, in computational materials physics, and also with a strong connection to application of AI and machine learning to these topics. So we want to hear everything about that, and we're really happy to have you here. Thanks.
Yeah. Thank you very much for the introduction. And indeed, for this talk, I'm purely talking in my capacity as a professor of physics. So I won't go into any details of university administration, although I could talk about that as well. But this is a purely scientific talk. And indeed, this is an overview of what we have been doing regarding, well, first of all, what is fusion? Why are we doing this? And then about how to use machine learning approaches there. And here, I mean, in addition to me, key persons behind this work are Flora Jorabeko and Fredrik Granberg here, and also Jesper Byggmästare here at the Department of Physics, and then Aaro Järvinen, who is in the audience, who actually helped me quite a lot with the plasma physics part of this this talk. But now I'll go. To start the talk, those of you who know Finnish at least might have noticed that there is actually been lots of new exciting news about fusion research recently. It's one can say it's a hot topic, and you'll see later on why it's literally a hot topic. Yeah, just a few weeks ago, the largest running fusion reactor on Earth made a record in actual fusion energy production a few weeks ago. I'll give a bit more about that later on. And this topic of using machine learning, tekoäly in Finnish, so it has also had quite a lot of publicity recently due to a very exciting work done in Lausanne on this topic. And on this latter topic, well, I will present also a bit more technical detail about what that was about. But before I go on, I might just briefly tell who are we doing this. So we have two parts here. We have the Advanced Computing Hub of Eurofusion, and then our research group working physically at the Accelerator Laboratory building in Kumpula. We are about 25 scientists. Some of the pictures are a bit old because of the corona. We don't have pictures of all the new employees, but all the senior scientists are correct. So this has been mainly done in my group, and then actually to an even larger extent in the group of Flora Jorabeko, who is another professor here. But what I will actually now be talking about is I will give a fairly detailed introduction to nuclear fusion as a possible pathway towards energy production. I believe most of you are not experts on this topic, and to understand why machine learning and where machine learning approaches can be useful, I thought it's good to give some background. And then I'll especially point out that, okay, why don't we have yet electricity producing fusion reactors, and related to that how then the second part of the talk is really how can machine learning methods possibly help this, and it turns out they can help on many levels, but because it's only half an hour talk, I'll focus on the plasma physics and materials, some examples from plasma and materials physics. Well, but if we start from the basics, this is a very basic nuclear physics graph, which shows that when you have the nuclei, all at the nuclei of atoms, how much energy can you gain if you split the heavy nuclei up, or if you join light nuclei. And the current nuclear reactors all work with the fission reactions. That is, you have heavy nuclei which undergo fission, split up into smaller nuclei, and this leads to an energy gain. Fusion is the opposite. You have light nuclei which are joined together, and this also give an energy gain. And this curve is based on actual data. So you see that the energy gain for the light nuclei is actually much larger per nucleus than it is in the fission process. And on the other hand, as you know already, fission is a very efficient energy production in means of how much energy you get out per kilogram of fuel put in. Well, so that graph looks simple, just like take nuclei and start fusing them together. We'll get lots of energy, but there is also a very simple physics reason why this is not at all easy to achieve. The point of this is that if you remember from high school physics that nuclei are all positively charged. If you have two positive charges, they repel each other with a Coulomb potential, a repulsive potential. And this means that to actually get the reaction going, you have to get over this so-called Coulomb-barrier, and this barrier is quite high. It's of the order of mega electrovolts, and only after you get the barrier, when the nuclei are very close to each other, then you get the reaction and the energy gain to this. And now we start to get this why this is hot, because in a simpler language, high kinetic energy simply means a high temperature. Temperature is essentially just kinetic energy. But to look at it a bit more in detail, so if you want to produce fusion efficiently, you need a high temperature, and the picture of the sun is here for a reason, because all the energy produced in the sun is made by fusion, and you probably know that the sun is rather hot. But then you also want to have a high density, that is, even if you have a high temperature, if you don't have enough of them, it's not very efficient. And the third criteria, which is not quite as obvious, is that you need to have lots of time, and this is usually called confinement time. That is, the high temperature and the high density should be in the same regional space at the same time. And this time during which it occurs is called the confinement time. And this leads to the simple criterion for fusion, that the product of these, the temperature times the density times the time or confinement time, should be high. Well, in the sun, it's easy to understand why you get fusion. The temperature is high, the density is high, especially in the core of the sun, and the confinement time is literally billions of years. So you have plenty of time to induce the fusion. And it turns out that if you analyze what the sun is actually is, the temperature in the core of the sun is of the order of 10 to 50 million degrees Celsius or Kelvin. It doesn't matter in this context. But then, of course, we can make energy from fusion with thermonuclear bombs, sadly enough, and in them you use a regular nuclear weapon to induce an extremely high temperature and extremely high density. The confinement time is very low, but this product is because the temperature and pressure are very high, you still can get fusion. But obviously you can't use the hydrogen bomb approach for controlled energy production. So to get something controlled fusion on Earth, we can't have a very high density, because any reactor would explode if the density is extremely high. So the conclusion is that even though we probably can get macroscopic, or can get already macroscopic confinement time, still to get a reasonable yield, the temperature in the fusion plasma needs to exceed the temperature in the sun. So need to have temperatures higher than 10 million degrees and much higher actually to start getting a reasonable reaction yield. And now you probably start to understand why achieving this is not quite easy. Well, nuclear physicists have been doing this. Studying the reactions is not difficult at all. Actually, you need only a mid-size accelerator to start doing fusion reactions. Here in the accelerator laboratory, we can easily do fusion reactions by taking a suitable ion beam and shooting it at a suitable target. The yields are just ridiculously low, so it's completely useless from an energy production point of view, but it's not difficult to do with fusion per se. So people study these reactions, and after going through hundreds of possible fusion reactions, turns out the one which is easiest to achieve is the reaction between deuterium and tritium. These are nuclei of the hydrogen, which can have a pretty high reaction cross-section at a fairly low temperature. So this is 10 keV here is 100 million degrees temperature in regular temperature units. And the maximum is at 70 keV, so that would be 700 million degrees C. But if you achieve this reaction, you get energy production by a factor of 250, which is quite high. It's also 4 million times higher than if you do the chemical reaction between deuterium and tritium. So this is why this is really a very efficient means of producing energy if you start achieving it. As I said, it's the stars and the sun. All stars work by fusion, and we can do it with accelerators or in weapons. But the difficult part is to do it in a controlled manner, which is also gives actually energy in a reliable way. And there are many approaches which have been tried for this and are being tried. There is, I won't even go into details, but there is a long list. You may have heard something like the bit older, you may have heard like 30 years ago, there was a big craze about so-called cold fusion. Well, cold fusion can definitely be ruled out. I mean, there is no reasonable fusion reaction going on there. It's probably some weird electrochemistry which was going on. But all the others are still in principle on the list. But for this talk, I won't go into describing the alternative concepts. I'll focus on the concept which we know can work. It may be very expensive, but we know at least in principle it can work, and it has clear roadmap to how to get the actual energy production, and that's fusion tokamaks. Well, then the other question is, why is it worth aiming for when it produces lots of energy? The fuel, deuterium is very easy to obtain. Regular water you drink from the tap has deuterium in it. Tritium is a bit trickier, but you can obtain it from lithium, which, as you know, is in your mobile phone batteries and so on, and you wouldn't need a lot of lithium to run a fusion reactor. And then one huge advantage, it's safe. I mean, these tokamaks, they are complicated machine, but they have the inherent feature that if you have a serious disruption, it stops the reactions within seconds. The worst thing which may melt is that happen is that the inside of the reactor may melt if it goes really bad, and then you might have to stop the reactor and change parts, which could take a long time. But there is no risk that the whole thing would explode in any way outside, because you can the reaction stops itself when if there is significant melting of the reactor inside. And there are no harmful greenfield gases produced, and there is no long-lived radioactive waste from the reaction itself. There is some activation inside the reactor, but it's not the actual reaction products themselves which do that. But you need, as I pointed out, you need a high temperature, and at these high temperatures, around 100 million degrees C, all matter is in the form of a plasma. And a plasma again means that you have nuclei and electrons which are completely decoupled from each other, and this plasma is what you need to control and get to keep at a high enough temperature to form a fusion. And this tokamak concept starts with what's known as magnetic confinement. That is a strong electric and magnetic field which can keep plasma inside a cylinder with by having suitable electromagnetic circuits around it. But making this cylinder is relatively easy. It's called a linear plasma machine. The problem is that what happens at the end of the cylinder, and it turns out that there are huge energy losses at the end of the cylinder. So ideally you would want to have a cylinder without any ends, and the solution to that is to bend the cylinder around to form a torus. So you make a ring out of this, then there are no ends, and you have no energy loss at the ends. And this is the basic idea of the tokamak, which was invented by the Russian scientist Sakharov and Tam in the 1950s. Sakharov, as you know, probably know, was then later on a Soviet Union dissident. But they came up with this concept, and in the 1960s it was published internationally, and then It has been developed in most major countries on Earth. When it's running, you have a very hot plasma in the middle and then a colder one on the outer side of the torus. And there are many tokamaks around. The largest one, which is now running, is this jet in the UK. And here you see the scale. This is a human, so it's quite about 5 meter high thing. And to give an idea what this looks like, well, let's see. Oh, yeah, let's hope that this one runs. Okay, I have 2 videos here, and I'll try to show the newer one. Okay, yeah, now it's coming. This is from YouTube, so. Yeah, so that was the record-breaking event from a jet which I mentioned, which was done a couple of months ago. They produced 59 megajoules of energy in that one for 5 seconds. 5 seconds does not sound like a lot, but it was actually the world record in a sustained energy production. And if they had the capability to keep up the heating, they say that they could have run this in principle, well, maybe not forever, but for a much longer time. They just run out of heating power. So as a proof of concept, it was very important. Well, I'm slowly getting to the machine learning part. So once you have this running, then the idea is that this would run like a regular power plant, coal-fired power plant, or regular fission nuclear power plant. You have the fusion running. It would heat up fluid, water, or maybe lead or something else, and you have a heat exchanger, and then you produce electricity. So it's except for the fusion power plant, fusion itself, there is nothing magical. Well, people often say it's always 50 years in the future. Well, now we say it's 35 years in the future. So we have made progress. Important thing to consider is that there has been progress of about 5 orders of magnitude in the energy production, and ITER, which is the large reactor now under construction in FART, would be very close to the reactor conditions. If one makes a bit of improvement in the plasma, it might be that the ITER can produce energy as much as you would need in a power plant. But so the basic concept in tokamaks is clear, and the ITER, which is now built, should produce energy by a factor of 10 to 20 for an hour or so. And there are already designs for an actual power plant demo, which could produce by a factor of 50, which should be enough for commercial energy production. But still, what are the challenges? Well, first of all, building it is quite a thing. It has to be like 20 meters tall. You have interesting cooling problems. The plasma will be 100 million degrees, but about 2 meters away from it, you need superconducting magnets at 4 kelvins. So you need to have a cooling from 100 million kelvins to 4 kelvins in about 2 meter distance. I always thought as a physicist that would be a complete showstopper, but the engineers I've been talking to, they say, that's actually quite doable. So at least on this part, the engineers seem to be know what they are doing, and it is working in, say, jet and so on. But then the really difficult parts are related to the plasma physics, how a plasma would operate in a machines not yet built, and then the materials. What happens when you have the hot plasma will a little bit touch the materials. It's not possible to confine the plasma 100%. And even if you have only 0.1% of the hot particles coming out, that can still be an issue for long-running productions. The other thing is that the neutrons from there can degrade the mechanical properties. And then there is the issue of how to make the tritium, but today I won't go into that. But yeah, now I'll give a few examples of what has been done regarding machine learning, and first the plasma physics part, and then later the materials physics part. And this plasma physics part, as I mentioned in the beginning, the main key expert in this topic is Aaro Järvinen, who is in the audience. So I'm sure that if you have questions, Aaro will be happy to tell you more details. But anyway, one of the challenges in the plasma control is to predict and avoid plasma instabilities, which are called disruptions. Because if you have an instability disruption, it can melt the wall. This is on the inside, so as I said, it's not really a safety issue, but still, if you want to run a reactor a long time, you don't want to have this happening and the reaction stopping every now and then. One can try to predict disruptions from first principles, which means that you really simulate the plasma physically with a very as realistic plasma model as possible. But these are very, very heavy simulations, are very challenging. And because of that, people try to use data-driven approaches. That is, they collect data and then train some machine learning algorithm to predict when will a disruption occur. And if this prediction is fast enough, then the point is that one can still adjust the plasma operations or do some cooling, rapid cooling by shooting something in the plasma, for instance, which then may be able to allow the disruption and allow the operation to continue. And this is some of the many approaches which have been used for these neural networks, decision tree methods, and so on, and so on. And also a partly related issue is to understand the plasma turbulence. That is, the plasma is not fully homogeneous. There is turbulent features in there. This can be simulated first principles. This has been done in Finland quite a lot with a code called Elmfire, developed at Aalto University of VTT. They can model this, but the problem is that to do these kind of simulations, you need like a year of simulation on a high-performance computer. Because of that, people have used reduced models, which are simplified plasma models, but even they take several hours on multiple processors. And now the hot topic is to then use neural networks, so-called surrogate models, which allow speed up also from the reduced model to do this on a second time scale. And this is again something which now you are on the time scale when the plasma machine actually operates. So this can allow you to do on time control while the routine is operating. And also Bayesian methods have been used for integrated analysis of fusion data with, for instance, looking at the temperature and density profiles. Again, on the disruptions, that there are very recent work on using deep learning for predicting the disruptions by doing a tomographic reconstruction in a small fraction of time required for the full algorithm. And here is a summary. I won't go into detail, but this is a summary that how machine learning tools may be used for enabling fusion power. Enabling fusion power. So the idea is that you have machine learned enhanced control. You want to sustain the high fusion performance. You measure during the operation with real-time sensors what is going on. With machine learning, then you do a system state analysis, classify what's going on, and if it seems to be, for instance, a disruptive occur, then you can feed this to the control module of the plasma, and then actually modify the plasma while during operation to prevent disruption and to optimize, in general, the energy production needs. And this is something which is a clear aim. It's certainly not finished yet, but like, for instance, this breakthrough I mentioned in the beginning is one example that people are getting close to being able to do this. But then the final 5 minutes or so of my talk, I'll talk about the materials physics challenges. And this is where our lab at the Helsinki Accelerator Laboratory, we are experts on this. In general, I have actually spent like 25 years of my career simulating what happens when a fusion plasma or neutrons from it interact with the reactor materials. And this here is a very simple example of what may happen. This is a single particle, heavy particle coming from a sample and hitting a material. And this here you see how the atoms move when this hot particle has hit a material, in this case copper, and you can sputter out atoms from here. If these sputtered atoms go to the fusion plasma, they cool the fusion plasma down. So it's not really what you want during sustained operation. On the other hand, this sputtering and particle emission is then what makes it inherently safe, because if you have a major disruption, you will have lots of particles coming out, which would then cool the plasma. Well, this example is actually not fusion specific. Copper is not going to be used in fusion reactors. It has too low melting point, but the physics is very similar to what happens in a fusion reactor. And currently, there are many materials which you can build a fusion reactor. ITER is being built and so on. But we know, for instance, ITER is built mainly with regular stainless steels, which we know that if you would try to run ITER as a power plant, it would take maybe 1 or 2 years after the neutron damage would be so high that you couldn't use it reliably. Most likely something would break there, and some parts would break and fall in the reactor and make it unusable. Well, that's not really a problem for ITER, because ITER is not planned to be used continuously as a power plant. So ITER will last long enough, but in a power plant, we know that we need better materials than what currently are used. So this, well, I could talk 2 hours just about regular modeling of this, easily. But now I'll focus on how machine learning methods have been used on the materials physics side. For instance, already some 15 years ago, Flora Jorobekova, when she was a postdoc in Belgium, she started using neural networks to get transition barriers efficiently during a fusion or fission reactor condition. When materials are subjected to long-term neutron irradiation, there is a risk that initially homogeneous materials, some elements start to segregate, and this will change the materials properties, which is not desirable. Also, more recently, in the last 10 years or so, in Flora's group, they have developed a new code to model surfaces under very high electric fields, also using neural networks. This is partly related to arcing in fusion reactors, partly actually related to stuff happening in accelerators and so on. But most recently, in the last few years, in Flora's and my group, we have been working on developing interatomic interaction models to be able to model really this materials interaction and the dynamic processes like the one I just showed you more realistically. We are not the first ones to do that, but I'll tell you what our addition to the field was. So I'll give a little bit of background. What we want to do is we want to do actually this is a very fundamental issue in materials physics and chemistry, model how atoms interact with each other. And people have been working on this since the 1930s, when people started knowing that, okay, there are atoms and they interact with each other. And initially, the way to model interatomic interactions was very simple pair potentials, like 2 simple exponentials, where here R is the interatomic distance. Nowadays, these analytical functions are more advanced, but they still are, most cases, you can write down them in 5 or 10 equation lines. Well, they have the advantage that they are very fast. One can easily simulate millions or even nowadays hundreds of millions of atoms with them. Well, on the other hand, since the 1970s, people started using quantum mechanical models to do the same thing. And this works, but the problem with this is that all the reasonable quantum mechanical models, they scale with the number of atoms squared or third. This means that if you want to simulate a large number of atoms, you just die in computational efficiency. So in practice, with the good models, you can do a few hundred, maybe a few thousand atoms sometimes, but not much more than that. And for most of these radiation effects, you want to use millions of atoms. But then about 20 years ago, people started looking at using machine learning methods trained on this density functional theory data. These have look like they can be a very good, not even compromise, but a way to get linear scaling, but with at the best case quantum accuracy, the same accuracy as DFT. There are many approaches done. This was a graph starting from the classical potentials, how machine learning potentials have started emerging. There are several neural network potentials and so on, deep tensor methods. But now I'll focus on what we have done with what's known as the Gaussian approximation potential to give a bit of technical detail. Sorry, I think I'll run about 5 minutes over time, but I really want to tell this and give a bit of more detail on this. So to get the machine learning potentials, you need the machine learning approach, but you also want to have some insights of the basic physics and chemistry of the system. Because you could, in principle, just take atom coordinates, run a huge neural network on it, and try to get the energies, and that can, in principle, be done. But the point is that we know some basic physics and chemistry. For instance, if you have two atoms in vacuum, you know that the energy, if they're at the same distance, the energy has to be the same no matter how it's rotated. So if you only train on atom coordinates, you might very easily end up in a situation that different rotations give different energy, which is physically completely wrong. And it would be quite stupid to do it, even if in principle you could do it. So because of this, people started using descriptors to quantify the local atomic environment, and this way take into the basic physics insight into use before you do the machine learning. And now I'll spend a couple of minutes describing this. So the point is that we know from chemistry basically that atom energies of an atomic system should be invariant to translation. That is, if you have these two atoms, if you move them in vacuum to another position, they should have exactly the same energy. Then rotation, I already mentioned. If you rotate it, it should have exactly the same energy. Then permutation is a bit trickier, but that is if you have more than two atoms and you change the atom types, but have the same angles between them, for instance, then you still should have the same energy. But people have been working on this, first maybe mostly the group of Baylor in Germany, and then later a group in Cambridge, Gabor Shani and so on, and come up with a fairly good framework for doing this. So instead of looking at the atom coordinates, you start with the interatomic distances. Then you have a three-body descriptor, which means basically that you use the angle between the bonds. Then you use symmetry functions. This is a bit more complicated, but this essentially is related to this fact that if you rotate it, you should still have the same energy. And then a third thing, fourth thing is that you want a smooth overlap of the atomic position. That, well, this roughly speaking means that if you don't do this, can end up and you still have only a few tens of thousands of DFT data points, you can end up in a situation that if you shift the atom position slightly, the energy wiggles. Whereas from the chemistry, we know that if you just change an atom position a little bit, the energy should be also changed a little bit, and it should be a smooth function. And this smooth overlap of atomic positions basically means you sort of fictitiously spread out the atom positions, and this allows you then to get them avoid this issue here. And then after this, you do a Gaussian process regression to get you have a exponential Gaussian kernel, then sum this up with the regression coefficient. So this is essentially the machine learning part after you have formed these smooth overlap positions. But our addition to this is that the gaps existed, and they were for some materials like silicon, tungsten already pretty good. But we figured out when we got interested in this about 5 years ago they couldn't be used for radiation effects relevant to fusion reactors. Because the original gap potentials were not trained in any way to the short interatomic distances, which means that you could get completely random results. And this, of course, relates to the fact that machine learning generally cannot extrapolate. So if you try to do an extrapolation, this could really horribly wrong. On the other hand, we knew from our previous work that you can actually get with the other DFT methods, this short-range part to a 1% accuracy quite simply without machine learning. So what we did is that we modified this gap formulas to add these realistic, which we knew to be realistic pair potentials to describe the short interatomic distance as well. And okay, now for the sake of time, I'll skip the details, but basically just tell you that these graphs essentially show the approach works, and we can get a very smooth overlap and get the high energy repulsive part fully correctly, which it wasn't without. So this is showing some small interatomic separation. This was the previous model. You see that it's quite weird results, not repulsive enough. This is the DFT data, and this red curve is our model. So you see that we essentially get a perfect description of the short interatomic separation. And what we have done is we have, I'm getting to the end, don't worry, 2 slides more. So what we did is one of the things this approach actually enabled with some modifications, still a numerical tabulation of the many body part of this, is that we could make an interatomic potential for a 5-element high entropy alloy. And this is something nobody had managed to use any of the previous approaches to do a 5-element alloy. At most people could do about 3 elements. We tried it as well, and we failed to go to 5 elements. But thanks to this machine learning formalism, a very smart addition by Jesper Byggmästare, additional modification to the formalism, we can essentially reproduce extremely complicated alloys to very high precision. And Jesper Byggmästare, by the way, is a postdoc at FKI. I mean, so he's really working on further developments of this now. And okay, now to just my last slide. So after doing all this work, which we finished just about a year ago, and now still are continuing to improve the models, we could use them for production runs. And one of the many things we have studied so far is that we study if you have a void, an empty space inside a material, what happens on the inside of this empty space. This is something which may happen in reactors. And it turns out that in this high entropy alloy, if you have a void, instead of having a random atom configurations around the void, niobium is strongly enhanced at the inside of the void, which is, and then also to some extent vanadium is enhanced in the vicinity, which is something which we couldn't have done this study without these machine learning potentials. And now this is something which may then affect the stability of the materials in the long term. Okay, so sorry to overrun the time a bit, but just to conclude, so I hope I convinced you that at least in principle, fusion is one of the extremely few energy forms which could work huge amounts of energy for really long time, so without any significant environmental problems. Of course, solar, wind, and so on is also are also very good, but there are still limits for how much solar or wind energy you can do. And but there are still things to be solved before this is running, but we are doing it right now. And these examples show that, just to simplify it, that the machine learning can be used in actually a lot of the parts of this. And this advanced computing hub we now have in Helsinki, led by Fredrik Kamber, has about 10 people working on exactly these issues. So we are really a major effort going on here right now. So yeah, thank you for your attention.
Thanks for the talk. Yes, it's super interesting. There is there will be a lot to talk about. First of all, maybe if there is any question from the audience. Otherwise, I have a few. You can raise your hand or write on the chat. If there is nothing at the moment, oh yeah, there is already one. Dennis.
Yes, I was wondering how many particles did you have in the simulations? you said it like you can boost a lot the computational power, but you were talking about this few body case.
Yeah, I mean, okay, the descriptors describe in a local atomic environment, so you go maybe to 10 or 20 neighbors, but that's what required to do the linear scaling. But after you have done that, then you can scale it up. And with the machine learning potentials, the largest, they are still slower than the regular ones. So the largest systems we have done is of the order of 100,000 atoms. But that's large enough to many radiation effects already. Then with the analytical potentials, we actually literally have done hundreds of millions of atoms. So for those, the limit starts to be not the computer capacity, but the computer memory. But yeah, I mean, with these machine learning methods, let's say 10,000 is with this gap approach is quite doable and for hundreds of picoseconds or so. Okay, hundreds of picoseconds may not sound like much, but actually on the atomic scale, 100 of picosecond is quite a lot.
And did you try to use to approximate some ab initio method instead of DFT?
Well, I mean, okay, some people call DFT ab initio, some people call it an approximation, but anyway, I mean, in principle, one could, if you mean by ab initio, you mean the Hartree-Fock configuration interaction or something like that. Yes. I mean, in principle, they could be used. It's just that you need to do the training. You need thousands of data points and include a liquid configuration, which have to make a reasonable liquid configuration, you need a few hundred atoms. So to do a few hundred atoms with a configuration interaction is quite a challenge. So that's why most people are, or basically everybody is using DFT approaches. Some are, if you really want DFT accurately, you can use the hybrid functionals, which make them quite precise. So I think most people would agree. And also you can compare, of course, with experiments. And it seems that modern DFT methods, not the standard original one, but the more modern DFT methods, you can get very good agreement on experiments on a wide range of properties.
Yeah, because I said in this high energy state, these atomic effects or quantum effects are of big importance.
Yeah, obviously. That's a good point. When I mentioned this DFT DMOL method, when you want to do the repulsive potential, you can't use standard DFT. You have to, because the inner core electrons will be excited. So what you have to do is you have to do all atom DFT. And that's what this DFT DMOL, all electron. So you need to have all electrons free to and optimize the electron density of all electrons. That's what this DFT DMOL approach has done. And pretty recently with Tage Sundholm, we have actually used even more advanced methods, which were finite element functions and so on. But they seem to be accurate. I mean, the DFT DMOL seems to be accurate to this 1% I mentioned.
All right, thank you. I will stop here. It was very interesting talk.
Okay, we do have other questions, and actually, yeah, the question in the chat mixes with the one that I wanted to ask. So yeah, I can go. And the methods you were talking about, let's say, I mean, at least most of them are surrogate-based model in the sense that you use machine learning to model these other computation, which would be actually hard. And, machine learning can allow, say, you to do things faster, say, to go to high dimension. So if you have any comments, say, comparing this approach that you've been talking about to run based on reinforcement learning, like the recent DeepMind results, if you have any comment about that.
Yeah, I think I probably gave that word over to Aaro Järvinen, and he knows that part better. So, Aaro, do you want to comment on that?
Yeah, sure. I can pitch in here. So, yeah, so that's a high-level result that was published in Nature less than 2 weeks ago. So I think it was 16th of February that the paper came out, and then they had this big news announcement about it as well. So it's basically a collaboration study with the DeepMind, which I suppose everybody here knows very well, and then the team of the Swiss Plasma Center at the École Polytechnique Fédérale de Lausanne, TCV Tokamak. And yeah, I mean, this is certainly the the way towards the future of developing the machine learning enhanced control in fusion reactors. So it's a pretty exciting study where they basically were able to use this reinforcement learning algorithm to basically train to control the magnetic configuration in the plasma. And then they had a demonstration where they were able to pull some pretty exotic magnetic configuration after they have trained the algorithm to do that. So you can find a lot of details in the Nature paper about the study, and yeah, I'm very excited to see that type of work happening in the field.
Okay, thanks.
Yeah.
I think we can. Unless there is anything else very quick, I think we can wrap up because we are
Well, there is a notice 10 wrote that question. I can still answer to that about this high fidelity with cheaper load. Maybe, but one would have to be a bit careful because I didn't emphasize it, but when you train this gap potential or something, it's very important that the data set is consistent. That is, if you take different DFT varieties, you can easily get small differences, like say 0.01 or 0.02 electrovolts on practically identical configurations. And if you try to train then a gap or something else on that one can again get this. Well, it's difficult to train. It's difficult to get the training to converge, and then it could lead to these results that again you don't have smooth representation. So not okay. I'm sorry, I haven't read your master's thesis, but I would be a bit careful about doing that because, or at least then consistently use the with the lower fidelity once again for the final training set. Then it probably would work.
Yeah, of course, with the fusion reactions, there's like so much going on, and the continuum of things it makes things more complicated. We studied this only for like material research, so there I think the risks are lower.
Yeah. I mean, for fusion or any non-equilibrium effect, you need to definitely model the liquid phase. And liquid, because it has more or less random configurations, one can run into these troubles easily.
Okay, so I think we are done. Thanks again. Fantastic talk, very interesting discussion, and yeah, really looking forward to see the advancement in this field. It's really exciting, really important. And thanks again.
Thank you very much. Bye bye.
Okay.
Thank you.
Bye.
Bye.